reproducibility crisis, because I think a lot of the issues that we are seeing with regard to analytic flexibility are centered around concerns about reproducibility. And so I've just sort of highlighted a few studies here that I think have been really important in our evolving discovery and discussion about reproducibility issues. And many of you know that a lot of these issues have permeated into mainstream media outlets, which always complicates the discussion and makes things, you know, a little bit more challenging. But as this very, very perfect tweet encapsulates, I don't want to talk about the dead salmon anymore. I don't even really want to talk about the reproducibility crisis anymore. You know, the great thing about our community is this community and the fact that we have always taken challenges and used them to move forward and identify really good solutions. So for the rest of this talk, we're going to talk about the reproducibility opportunity. A lot of us are really concerned about what we are doing with our own pipelines, and I want to focus on the future and what that might hold for us. But in order to talk about the future, I'm going to actually bump back way to the beginning of our field. And so the historical perspective here is that way before this reproducibility crisis, we were interested in consensus across studies. And I've highlighted a couple of what I call proto-meta-analyses back in 1993 and 96. These were functional PET meta-analyses that really looked at variability and activation across cingulate gyrus and anterior cingulate. And the point here is simply that we've been very interested in our variability since the beginning, the dawn of the field of human brain mapping itself, and we've used meta-analysis to really help us identify consensus, because we know that any single neuroimaging study has some limitations. We have a literature full of small, non-representative samples. We know that in the case of BOLD, we're dealing with an indirect measure of neuronal activity. We have a literature full of isolated findings. We don't replicate our work enough. And we know that there is always going to be variability associated with differences in experimental design. But now we also know that there's variability associated to our analytic pipeline, and that's what we're going to kind of focus on in this particular symposium. So, for those of you who are Marvel MCU fans, welcome. We are going to start our journey into the analytic multiverse, so let's join hands with Loki and Sylvie and, you know, talk about what we're actually dealing with here. And to do that, I'm going to start with the CARP paper from 2012. This was our first awakening of what analytic flexibility actually means for us in this community. And in this particular paper, he used a single event-related fMRI experiment and analyzed the data using multiple different methods. He identified 10 different analysis steps, and each had 2 to 4 different strategies. This yielded nearly 7,000 different pipelines. And all of the activation maps that were produced were corrected with 5 different thresholding approaches. And so at the end of the game, we're talking about nearly 35,000 maps that were produced for this one data set's analysis. Now, okay, some regional results were stable across pipelines, but overall estimates of peak activation strength and statistical significance were highly variable across pipelines. This was a big deal at the time, and I'm going to fast forward a little bit to 2020, which gave us all so many gifts. But the one really, really great gift for us was the NARP study. NARP stands for Neuroimaging Analysis, Replication, and Prediction Study. And in the NARP's paper, 70 independent teams analyzed the same fMRI data set to test 9 different hypotheses. Now, what was really interesting was that no 2 teams chose identical workflows, and that really gives you a sense of the scope of analytic flexibility, right? If you just throw a whole bunch of people and analyzing the data, that no one's going to come up with the same pipeline. They observed fairly large variation in results for the results of addressing the hypothesis tests. And this was true even for teams that had highly correlated maps at intermediate stages of the analysis. Now, there were a couple of key aspects of the analysis methods that it seemed to be more sensitive to variation in results. And one of the important things I want to note here is that meta-analytic aggregation was really helpful in identifying consensus in activation regions. So let me delve into some of this a little bit more deeper. And you know, I chose not to go to the video route here, but I have a really cool video here where we've got the main timeline that splits out into various pieces here. The idea is that with NARPs, we learned that you can take the same data set and the same set of hypotheses. And different groups are going to give us different answers. And it's hard, if not utterly impossible, to identify reproducible findings with a single analytic pipeline. And so that really means that the array of analytic approaches that are available to us is so vast and so flexible that it really is our own analytic multiverse. So I talked about there were a couple of key aspects of stages and steps of the analysis that seemed to be a little bit more sensitive. And those were found to be spatial smoothing, which is actually a little bit of a complicated issue, so I encourage you to delve into the paper to learn more about that. Multiple test corrections, we know that's an issue, right? Denoising and software package. So shout out to all of my what if fans here. I also want to highlight parcellation. That wasn't really explicitly addressed in the NARPS paper, but we all know that parcellation matters. It has an incredible impact on our papers. And so I want to very much highlight some interesting work that's being done by Ruby Kong. Her poster is today and tomorrow. She's really looking at correspondence across 16 group-level functional brain network atlases, and I think that this is really the first step in understanding the impact of parcellation, just to really understand the correspondences between the atlases themselves. Okay, so inevitably, now that we're having this conversation, what I hear most often is, great, it's fabulous that we know this, knowledge is power. What are we supposed to do about it? How am I supposed to handle this in my own analyses? Or as Mobius M. Mobius says here, what's reviewer 2 going to say when I submit my own paper for peer review? And the reality is we don't have all the answers yet, and that's tough to say, right? We're scientists, we like to have some answers. But I always think that the very first step in acknowledging, in moving forward and finding solutions is to discuss it as a community. And so that's what we're doing here today. We're bringing attention to the issue, we're having a conversation, and that's always the first step. The other thing that I want to say is way back in the CARP paper, there's a really great quote. To mitigate the effects of this flexibility on the prevalence of false positive results, investigators should either determine analysis pipelines a priori, pre-register your analyses, or identify optimal pipelines using data-driven metrics. If researchers use multiple pipelines to analyze a single experiment, the results of all pipelines should be reported, including those that yielded unfavorable results. And that's tough for us sometimes, right? But it's really, really important. And then I also want to highlight a tweet that I saw earlier this year that very much resonated with me. Again, what I love most about OHBM is our community. And we have a long history, decades now, of our methodological researchers making tools for us to make our analyses more accessible, to make our analyses better. And right now, we have some really exciting work that's being done, developing new analytic approaches, developing software to help us with this multiversal problem. And so that's the bright future that I think is headed our way. So a couple of things in thinking about that. One of the things that the NARPS paper did is they used meta-analysis. They used both image-based meta-analysis to assess consistency across teams, showing that inconsistent results at the individual team level underlie consistent results when the results of the teams are combined. And so if we are going to go down this very complicated multiversal pathway, then we're going to need meta-analysis to help us aggregate our results and show us where analytic flexibility gives way to consensus. And I do want to highlight a tool that was used to assess the coordinate-based meta-analysis results of the thresholded maps in the NARPS paper, and that's NIMARE. NIMARE stands for Neuroimaging Meta-Analysis Research Environment. It is part of the ever-growing Python ecosystem, including NARPS and NiLearn and NeuroSynth. I want to highlight this here. It has both tools for image-based and coordinate-based meta-analysis, and special shout out to Taylor Silo, who is the lead developer for NIMARE. Okay, so our field is transitioning to a more replicable future, and we've got progress on several fronts. Our sample size continues to grow. We've got pipelines and containerization technologies that are becoming more accessible and more prevalent. And we're pre-registering more of our analyses, and we're adopting the format in our manuscripts for register reports. But we still have many unanswered questions, some of which are going to be addressed in this symposium. How severe is this flexibility? Some of us want to just avoid it, and some of us really want tips and tricks for managing it. But is this computationally feasible? And are the computations accessible and equitable for all researchers? Is it sustainable? Once you have your multiversal results, how are you going to examine them and summarize them? And then, should reviewers and editors be asking you to do multiversal analyses in your papers to show that your results are robust? So I want to leave you with 2 quotes from He Who Remains. The first is, you know you can't get to the end until you've been changed by the journey. This stuff, it needs to happen to get us all in the right mindset to finish the quest. And, we are currently at a really messy, chaotic point in our field where we know we have this problem and we're not really sure of what the solutions are. But that's okay. We're in the mindset now to finish this quest and move forward and make our analyses more replicable. And then the last quote I want to leave you with, seriously, I love this character, he's amazing. We're all villains here. We've all done horrible, terrible, horrific things, but now you have a chance to do them for a good reason. And my point here is that, look, some of our analyses, maybe looking back, aren't quite as robust and reliable and replicable as we wanted them to be at the time, as we thought that they were at the time. And so in some cases, maybe we are the villain of our own story. But again, what is important is moving forward into the future and really focusing on being transparent with what you've done and what you have observed and what your findings are, and leveraging the available best tools and practices for open and reproducible science. And so in that sense, again, I'm optimistic. I think there's some good stuff headed on down the road, and I, at this point, will hand over to the next presenter. In the rest of the symposium, we're going to have 3 presentations. Camila is going to tell us about reviewing neuroimaging flexibility, components and records of provenance. Tom's going to talk to us about statistical approaches to multiverse analyses. And JB, who unfortunately can't be here in person, is going to talk about solutions for analytic flexibility, and things that we're interested in is towards better publishing. So with that, I will hand over to Camille. Thank you.
Thank you, Angie. Just want to remind everyone to use the app to ask questions.
Thank you. So, hi everyone, my name is Camille Momé. I'm a researcher at INRIA, and in this talk I will focus on reviewing neuroimaging flexibility, so understanding what are the components of that flexibility and how recording provenance can help us understanding what's going on in there. So, by way of an introduction, we'll look at the different types of analytical variations that create this analytical flexibility. So here on the left, you have a typical brain study. So we start with a phase where we are acquiring some data, then we're going to prepare the data with maybe steps such as denoising, registration to a common space, and so on. We get our measures of interest, the derived data here, and finally, by doing a statistical analysis or machine learning algorithm, we get the chance to answer our research question. But of course, in practice, it's much more complex than that. And the pipeline looks more like something like this. We have a series of steps instead of having just these 2 high-level steps that comes one after another, or even sometimes in parallel. And those steps, you know them really well. So I've mentioned denoising earlier, segmentation, and so on. And in fact, for each of these steps, there are many choices we are facing when we're doing an analysis. So I'm illustrating here with the first step. First, we could have chosen a different algorithm. Often there are different methods available to do the same thing, to do the registration, for instance. Or maybe we use the same algorithm, but there are different implementations across different neuroimaging software. Even when we use the same software, there are typically multiple versions available. Even when we look at the same version, we can vary the parameters to each step. And it has been shown that even when we have the same algorithm, the same software version, the same set of parameters, the software environment also has an impact on this analytical flexibility. And so I've illustrated here with 6 pipelines, but clearly we are in a space that is extremely big. And as Angie has been showing, we know now that depending on the pipelines, we can get differences in our results. And so the question here that I'd like to ask is whether we can understand why this is happening. And of course, this is a complex problem. And in my view, this is important for 2 reasons. It's important first because when we know that using a different pipelines, we get different results, this makes us wonder about the results we obtain with our single pipeline. So it impacts the reliability or the robustness of our findings. But it's also important in a world where we are reusing more and more data, working on open data sets, to question ourselves about how this can impact the reusability of derived data sets. And so here I just would like to point in different directions that can explain why we are observing this analytical variability. So first, there have been a set of studies, and I've put a few here as an illustration, that look at analytical variability as a type of variability that we would really like to get rid of. That's, for instance, the case with numerical uncertainty, or about different implementation in different software packages. If you have 2 software packages and you align the pipelines really well, you're expecting the same result, or roughly the same results, but at least you have the same conclusions for your paper. So this is really variations across pipelines that create variability that, as a community, we would like to get rid of. Now, sometimes, by varying pipeline, we get different results, not due to the pipelines themselves, but due to an interaction with the data. Sometimes, so what can happen is that the data set we have is not suited to answer our research question. And basically, when we go from one pipeline to another, we get very variable results because the data was not appropriate. Another case of interaction between data and pipeline is when there are assumptions violations. Sometimes the pipelines can work well in many contexts, but when used with a particular data set, it's going to fail. Maybe the level of noise was higher in that data set, and if you don't do the denoising step, basically your registration failed, and the results you're getting are just wrong. So, as I was saying, we see that we have some variability that is unwanted and due to the pipeline, some interaction with the data, and then the last bit of variability is, I think, what we are really interested in as scientists. This is the variability of interest. We are using pipelines because we want to understand what's happening in the data. And some models are going to be better fits than others. For instance, if I add age as a covariate in my model, the way I'm going to interpret my results is different if I remove this covariate. And so I think the problem of analytical variability is a bit difficult right now because it goes all the way from unwanted variability that we want to remove completely to variability of interest. This is what we care about. We really want that, to places where, depending on your data, pipelines are going to behave completely differently. And so in the following, I will discuss how recording provenance can be one element to help us understand and manage this analytical variability. So provenance, I've put 2 definitions here, is defined in Wikipedia as follows. Provenance describes how an artifact or a set of artifacts was produced. And in our case, artifacts are like brain images, brain signals, the type of data you're working with. In the context of this work, we're using the WC-Prov model for provenance, and they define provenance as information about entities, activities, and people or software involved in producing a piece of data. And I'll get in a bit more details in the following about what this entails in practice for us. So the first use case for me for provenance is to have an unambiguous description of the methods. So I think we've all been in that situation where we have a paper, and it looks great, and we really want to understand what's going on in there, but then we are just left with many questions. So I've put a few here as examples. Could be we're wondering about the release of SPM that was used. I'm not saying this is never available, but it can be missing, which registration algorithm, how was the brain mass computed, and so on. And there are so many details, we just can't fit all of that in our methods section. So the first use case for me for provenance is a question of transparency, being very specific about all the steps that were used and the different parameters and so on. And here we can link that to the idea of trying to reproduce exactly the same results, same data, same method. And to do that, we can have a description of provenance that is really high level. So here I have a simple experiment where at the top, as an input, I have a bits data set. I'm going to do a pipeline, and as an output, I get an activation map for a contrast. And so here my description of provenance is very simple. It's just saying I use this pipeline, and the code is available, for instance, in a Docker container. And this is a complete description of what was applied on the data. Now, I'm going to get a little bit further with another use case where provenance can help us. And I'm thinking here about dealing with unwanted variability. So we've said that analytical variability has many different reasons, and one of them is unwanted variability. So let's say, as a community, we realize that the parameters that was previously used is no longer considered as best practice. This happens all the time. Like our methods evolve, our understanding of brain data evolve, and sometimes we know that parameters that were used in the past were not best practice. Wouldn't it be great to be able to go back to the data sets that use that particular parameter, rerun the data, and see whether the results still hold? Another version of that is, well, we know that pipelines are implemented in software, and software have bugs. This is true not only in neuroimaging, but in any software that is produced. When a bug is found in a given version, same thing. Can we retrieve all the results that use that particular version, go back and check whether the results still hold? In order to do that, we need to have provenance that is a little bit more detailed. Instead of having just a pipeline that describes a single pipeline, we're going to have the different steps that were used with the input, the output, and possibly the parameters and the tools with their version. And this helps us understanding this particular use case when we want to deal with unwanted variability. Now, if we care about analytical variability and beyond the variability that we think is unwanted, we might want to explore which factors in that very large pipeline space actually impact our results. And this is also something provenance can help us with. So just like we asked earlier about the specific parameters that we know was no longer good practice, we could ask here, using this model, are my conclusions dependent on the size of the smoothing kernel that was used at step 5? So this is a very low-level question. But going a bit further, we might want to ask questions at a higher level. And to illustrate that quickly, I'll go back to a study that we ran with Alex Boring and Tom Nichols from University of Oxford, where we tried to reproduce 3 published functional MRI studies using 3 different neuroimaging software packages, AFNI, FSR, and SPM. The idea here was to align the pipeline as much as possible. And you can see here on the left the results for one of the data sets. At the bottom, you have the results that were obtained in the original study, and on top of that, you have the results with the 3 different software packages. And we can see that there are substantial differences in the threshold map. But as soon as we have that, the next question that we have is, okay, we've been aligning the pipeline, so what's going on here? Why can we see these differences? And in a follow-up paper, what we looked at is trying to divide the different differences that we knew existed across software. So we've identified 5. First, the pre-processing, the first level signal model, so this includes the href, orthogonalization, the first level drift model, the first level noise model, we know there are differences across software, and the second level model and inference. And by doing that, we can create pipelines that go from, on the left, 1A, a pipeline that is completely AFNI, up to, on the right, 7F, a pipeline that is completely FSL. And in the middle, we have mix and match between these two, plus fMRI prep for the preprocessing. So for instance, 5AF is using fMRI prep for preprocessing, first level signal model with AFNI, and the rest of the pipeline is FSL. And by doing that, we realized that between 7AF and 6AF, there was a big difference, and probably the first level signal model for that particular study was particularly important. And so going back to our provenance here, the question we've been asking are really at a higher level. Are my conclusions dependent on the type of noise model in the first level analysis? And to be able to ask this kind of question with provenance, we need both our detailed step-by-step provenance and a model that is going to tell us more information about each step. So here we could say the type of step that was used for step 3 is a first level analysis with that type of noise model and that type of href. And so here we've seen 3 different ways of doing provenance with increased complexity, but also increased richness in the type of questions that we can ask. We've been working on this as part of BitsProv, mostly on the first, so currently on the first 2 steps. And we're working on to making the step-level plus ontology possible in the future. So I want to thank everyone who's involved in this BIDS extension proposal, which is BIDS extension proposal 28, and all the contributors, both for their contributions, but also for very useful discussions that were used in, that helped me to prepare this talk. I want to thank also the ANCF and the BIDS steering committee and maintainers for great discussions on how we can explain why provenance is important in that context. Okay, so this is the end of my talk. I would encourage everyone to see our poster that is looking at how analytical variability varies with sample size. We are also hiring, and I would like to end by thanking JB for organizing this symposium, although he can't be here.
Okay, so next up, we're going to have Tom Nichols, who's going to talk to us about statistical approaches for multiverse analyses.
I'm going to try to work in the word multiversal as many times as possible. Let's see. Okay, so I'm taking up the challenge of now we have all these multiple instances of result. How are we going to integrate them? How are we going to interrogate them? And there has been some work on this, and so just this is the work that Camille was just highlighting. I want to say how proud I am of these little glyph thingies. I think they're a really nice way of summarizing the different pipelines, and you're free to use them as much as you want. So the question is, okay, fine, there's lots of differences here. How do we summarize these differences? Now, there's one thing you could just make a scatter plot, so take a pair of results and look at how similar or different they are. This is comparing the 2 ends of this extreme run of going from pure AFNI to pure FSL, and we can see there's a lot of variability, but that only considers a single pair of outcomes. So we could summarize this with a correlation matrix. And so, I don't know if I have a we do have a laser pointer, that's cool. Yeah, so that we can, from this, we can see on average, over the whole image, how similar are these. And what you can see from this, there's this block here, basically correlation 1, and that's interesting. That tells me that basically 4, 5, 6 are almost identical. And what is that? That's the first level signal model, drift model, and noise model. And that was something that we'd seen. Basically, the drift model, use whatever you like. Polynomials, DCT, it's the same. That's useful. But this isn't sort of a single result. It's still sort of a summary of all, it's still a bunch of numbers in a correlation matrix. Another approach that's been used in psychology initially, and that's been used in brain imaging at this recent, with this recent work from Bloom et al. From Columbia, this is a specification curve analysis. And if you're not familiar with it, it's really, really neat. You basically define a multiverse and a bunch of different ways of analyzing your data. And then, of course, this is not for imaging, but just for a single outcome. You then sort them by the magnitude of the effect. And then you use a bar plot, sort of a dot plot like this, to sort of decode these results. So here we can see they looked at the difference between just using the right amygdala, just using left amygdala, or bilateral amygdala. And you can see the ones that had the highest t-values are actually the ones that use the bilateral or the left only. And there are other sort of methodological options that you could have here. So this is a nice way to actually packing in quite a lot of information, and you often will see, you can pile on lots of different alternatives here, and often with these bar plots you can decode and see which things are giving rise to the results that have the greatest magnitude, and whether those things are good, and that maybe telling you, yes, I found the right sort of model options, or maybe you found some weird options that you wouldn't want to trust. The shortcoming with this is that this is just for univariate outcomes. It's not something that you can do at the image level. Another set of work that's proposed, this is just a preprint as of right now, DAFLIN 2020, which tries to find sort of a latent space of differences. So they were working in graph analysis of resting state fMRI data. And they looked at all these different approaches and looked at the intersubject similarity and then used a dimension reduction method. We can use several, but UMAP is the one I'm showing here, to understand what gave rise to the differences. And you see the biggest gradient here is between blue and red, and that actually turns out between the methodological choice of using motion regressor modeling versus global signal regression as an option. And each of these other sort of symbols will help you sort of explore and understand those differences. But again, this is really helping understand the differences instead of giving us a synthesis, a single summary. So what was motivated the work I'm going to talk about is the NARP study that Angie very nicely introduced. And this, again, took 70 teams who had to work independently. The different teams were not supposed to interact until the results were submitted. And then we had to provide answers, statistical maps, for 9 different hypotheses, and we had to give yes/no answers for these 9 precisely specified anatomical hypotheses. But the question that we had and we needed for the NARP study was like, well, what is the one answer? And you might think, well, what's the big deal? Just average it. Well, it's not really that simple. So while there is consistent variation, there's just, there's huge variation. These are the all 63 maps. There is some commonalities. How can we find those commonalities? Let's step back and look at regular meta-analysis. So regular meta-analysis, where we have k independent studies, you could say, well, why don't we just average the results? Well, if you average, the thing is, thanks to the law of large numbers, the more things you average, the more they will get small. So a null sampling distribution of a test statistic, a Gaussian test statistic, will be mean 0 and variance 1. But if you average 2, 4, 8, they'll get narrower and narrower. So that means you can't interpret it as a z-score anymore. Of course, the one good thing about this is that what it does mean is that when you average, the values get closer and closer to whatever is the common center. So this is kind of a problem if you want to keep on interpreting this as a z-score. And so there is a meta-analytic method. It's one of the image-based meta-analysis methods we have at our disposal, which is Stauffer's method. So Stauffer's method just simply multiplies by the square root of the number of things that multiplies the average times the square root of the number of things you're averaging to undo that effect, so that, okay, no matter how many studies we're combining, I can still interpret a z-score as a z-score because under the null hypothesis, the combined statistic will have mean 0 and variance 1. But what happens is that, of course, with more evidence, and if the mean is the same across all subjects, all studies, it grows, it gets bigger because, of course, well, it's square root of k there, right? And so this is good. I mean, this is, you're gathering more evidence. You have more evidence against the null hypothesis the more studies you're combining. So it makes sense that this test statistically is going to get bigger. But is that the right thing in a multiverse analysis? So I can guarantee to increase my z just by running more pipelines? That probably is not the right thing. So the number one sort of impediment to applying traditional meta-analysis methods is that they assume independence. Well, okay, for starters, in the NARPs, they started with the same data. And all of those different teams, here showing 64 different teams, produce statistic maps that are actually highly correlated. There's actually a lot of structure. It's actually, you might think, why, isn't it nearly correlation 0.9? You're like, no. There's some of these things that are getting up towards 0.8. Some things occasionally, they went in even opposite directions. And some are very lightly correlated. But we need to develop a meta-analysis method that can produce valid statistics when there is no signal present while still accounting for this correlation. So let me illustrate what that is, and then I'll show you the sort of the mathy details behind it. So the question is, with growing rate, with growing numbers of pipelines, what should happen? So I'll get to the details of how we account for the correlation, but for now let's just say that there's some effective K that we can scale that by, and that's kind of what it boils down to. Is it the right thing, the more different pipelines that we have, the t-values, the z-values should get bigger? That might seem wrong, but at the same time, actually, you're learning different aspects of the data. And if all of the different analyses are actually valid and are to be treated equitably, it's not weird that as you learn more information, you should get bigger z-scores. So maybe that's the right thing to do. Maybe in the tradition of meta-analysis, we should penalize inter-pipeline variability and basically attenuating this. Now, it still will get bigger, so it'll grow bigger with the more information, but you'll have a penalty for inter-study variation. For the NARPS project, I wasn't really comfortable with this, and we weren't comfortable that it would just grow and grow and grow. So we instead said, is there some way to develop a consensus approach? Is there some way to say that the map we get is going to sort of look like all of them? So basically, if all the studies maps have a given mean and a given spread over voxels, could our consensus map have that same mean and same variance? And that's what we were able to do. Basically developed a method that if there was well, first of all, if there's no effect, if all of the different pipelines are producing null, mean 0, variance 1, t or z values, what comes out is also mean 0 and variance 1. And then if there is effect, that basically we get that out. That is basically the same thing. So briefly, the details are here. The main result here is that we have to figure out what is the mean of the means across all of the statistic maps, and what is the mean variance across all the statistics map. And we're going to just jigger the algebra to make sure that the consensus map that we make, which starts out as just the average, so we start out by computing an average over pipelines, but we crucially we make sure the means are the same and the variances, and then crucially we have to adjust the variance. So we have to estimate the correlation across different pipelines or teams. Here, we will, for the work we did in NARPS, we are assuming that this is the same over the map. That is definitely a limitation, but it was the place that we started with. And crucially, if all this works, if there is no signal, the resulting consensus will still behave as a mean 0 variance 1. And then, since they're valid z-scores, you can do whatever you like, for example, Bonferroni or FDR. So this is just to give you an insight to the variability in the NARPS. This is just the first 32 images, and you can see there's a lot of variability. So I put a null Gaussian just as a reference. Some have very flat ones, some are showing positive, some are showing negative. There's a lot of there's a lot of variability here. And now you could look at each one and have criticism. You could dig in and say, actually, I think that team was using the wrong methods. But the goal here was to be completely agnostic and just say, no, I want to treat everything equally and see what would be the consensus at mean, such that mean has the same mean. The mean of that image is the mean of all these images, and the variance of that consensus is the average of all these variances. So we did that, and then that allowed us to do FDR thresholding, and you can see that there was actually very little consensus for one of the hypotheses. The one that had the most consensus was hypothesis 5 for the loss for the equal and difference case, where we saw these sort of medial frontal activations. So just to be clear, this is not. There are ways to more optimally combine these to actually have a more sensitive test, but that was not our goal. Our goal was to try to find something that was a consensus that reflected all the different things in an equal fashion. Okay, and that's where I'll stop. Just to stress, this is not the only way to approach metaverse analyses. There is a multiverse of different approaches, and this is just one way that tried to provide a single summary of all the inputs, treating them in a completely symmetric work. The things we definitely have to look at going forward is address the assumption of homogeneous correlation across the teams over space, and also really interesting work, I think, to look at the issues of developing like a random effects type inference that penalizes between study variation. So I'll stop there. Thanks. And with that, I would like to introduce JB, who is going to be with us in spirit and on screen now.
Good afternoon. My name is JB Poline, and I work at McGill in Montreal. And the last talk of this symposium is about the solutions for analytical flexibility and possibly the solutions in the publishing domain. My goals today are to, first of all, to remind us that most neuroimaging articles are published with results obtained with only one pipeline. And this evidence of analytical flexibility, while the evidence of analytical flexibility is rather overwhelming. The pipeline flexibility do give variable results, and the question is whether reviewers, editors should actually ask for complementary analysis to establish robustness of results as a variation with pipeline variability. And the question also is whether we should actually ask for a new norm of peer review and edition that considers analytical flexibility for whether we can publish an article in neuroimaging with the results of only one pipeline is now debatable. There's clearly a large context of irreproducible results. There's an interesting paper recently in PNAS showing that the number of the billions of citations and the millions of papers across all subjects in science are actually not providing a very quick turnover of key ideas and central ideas in the field, but really ossify the field as a scientific and stall the scientific progress in some ways. The number of unreplicated results is also a huge problem, usually attributed to small sample size or p-hacking issues or poor statistical training, but analytical flexibility is definitely part of that problem. So what kind of evidence do we have of analytical flexibility? I think at the moment there's a very strong evidence of p-hacking. And p-hacking is a type of analytical flexibility where the variation of the statistical model is actually yielding different results, and those results are cherry-picked. There's an increasing number of papers, however, on the variation of the pipeline and the variation of the results as a function of the pipeline, both, I mean, in fMRI, in T1, in diffusion imaging, and in other, for instance, connectivity aspect. But there's a poor response by the community. There's no simple fix. It's hard to redo with many pipelines the same analysis. So the question is really, what should we do as a community? I would also like to point to the fact that elsewhere in science there is issues in replicability and analytical flexibility, but in neuroimaging we are specifically touched by that problem. And I think one of the aspects that we can see in our field is the number of tools such as NiPipe and NiFlow and PyBra that are actually provided to make different pipelines using different type of possible workflow, piece of the workflows, or possible functions and possible steps of those workflows. So all those things are super useful, very important, and help us actually define what is the right workflow. But they also provide with a way of having a very strong analytical flexibility and do the cherry picking. There's a couple of possible answers already existing. I think the pre-registration is a framework that can be used to respond to analytical flexibility. Here in this pre-registered report by Vincent King in my lab, we looked at, we actually published the pre-registered report as a number of possible pipelines that will be done, and those pipelines were actually giving results, and we would actually ask for robustness of results across pipelines before deciding whether the result is consistent and robust. So in the context here of the involvement of the cerebellum with the in essential tremor cohort, this pre-registration is an interesting aspect where we could pre-register all the pipelines that we wish to perform on a specific data set for answering a specific neuroscience question. The machine learning aspect is also touched by the problem in some ways. Here, work by Jérôme Doques, showing that simple learners or versus complex learners in the UK Biobank, looking at the trying to predict the smoking status of patients, of subjects, sorry, showing that in fact those learners have a huge impact, of course, and the pipeline therefore has a huge impact on the results, on the predictability, but also the type of cohort that you select is critical for the result. And the last example from the lab here, from Nikhil Bhagwat, is the assessment of the correlation structure across subjects between region of the brain, so looking at the cortical thickness with different pipelines and tools, and showing that correlation structure is extremely different as a function of the cortical thickness tools that have been used for measuring the information. And so that is clearly something that is impacting the neuroscience results in the domain of the T1 imaging. So what are the responses? I will point to a couple of possible responses: neuroinformatics platforms, training and support, and possibly trying to change the publishing norms. In terms of the neuroinformatic platforms, this is a project by Jacob Sands-Robinson in my lab with Tristan Glattard also, and looking at how do we construct a platform that can launch a number of pipelines as soon and on a number of data sets, and showing the analytical flexibility as well as the replicability across cohorts of a specific questions, the result of a specific question here, the association between the hippocampus volume and the hearing loss. So please go and see his poster. I think that those platforms, if they become really usable and easy to navigate, will be one of the possible answers to analytical flexibility. The training aspect, specifically, for instance, being able to access a forum where pipelines can be discussed, the difference between results of pipelines can be discussed with the authors of the pipeline, the rationale why this is the case, and so on, is critical. And INCF is providing us with a great platform in that respect, which is the NeuroStars. So I would say that this is also part of the answer, is the training of the community on the specificities of the pipelines. And in terms of providing the community with possible ways of publishing differently, I think is also a key aspect and will be a key aspect of how we deal with that analytical flexibility. And those two platforms, NeuroLibrary for Jupyter Books or Aperture in a wider context, are both trying to publish pipelines in a way that makes it more easy to reuse those pipelines and also assess the validity of the pipelines across different contexts, scientific contexts. So a couple of maybe recommendations and takeaway messages. First of all, I think we should consider tools that will make it easy to study analytical flexibility. We don't have those tools yet, and possibly those tools themselves, studying analytical flexibility for a specific question, will become in the future themselves a publishing platform. Secondly, the use of standards in terms of pipelines and in terms of data sets and formats will reduce the burden in terms of launching different pipelines on different data sets. And that definitely is the sort of like the BEADS idea, or like any standard idea, and reducing the amount of required information in an article or required work to be done by a researcher is definitely one thing that we should promote and will help analytical flexibility, the study of analytical flexibility, and the robustness of our results. I would say increasing the training on these tools is really important. Increasing the community feedback and engagement on those tools is also critical. I would probably recommend to engage with INCF and all other standards organizations for pipeline publishing, such that the results of those pipelines on standard data sets can be stored and compared across pipelines. And also engage really with the publishing networks, so the networks of journals in neuroscience, Aperture, NeuroLibre, and so on, such that pipelines are published, and the recommendation for studying the robustness of the pipelines is being put to reviewers and editors. And in that case, in that sort of line of thought, engage with the OHBM Standard and Best Practice Committee and propose some analytical flexibility recommendation. I would like to thank you all. Wish I were here with you, and I wish you a very good end of the conference and end of the day. Goodbye.
Okay, now we have time for questions. We'll certainly welcome people to come to the microphones, but we'll start working through the questions on the app. Angie?
There are a lot of really great questions on the app, and I want to start with absolutely the two most important ones. Number one, shouldn't the he who remains quotes be dated at the end of time? And you are correct. That is my absolute bad. I am so sorry about that. We're also going to geotag those as beyond the void. So thank you for pointing that out. I'm going to address that in my slides moving forward. The second one is, how can we escape the multiverse of madness in fMRI? And man, you know we're not going to have an answer to that until after we see what happens to King and Quantum Mania. So you're just going to have to sit tight for that particular answer. Okay, but seriously, let's talk science.
Excellent. Well, first of all, thank you both for your talks, but Angie made me feel better about multiverse. I mean, usually, you know, I break out in a sweat a bit when I think about it, but you really, I think, have told us why we should not fear the multiverse. Should we consider only the overlapping result among different pipelines as the true result? That is, in fact, one approach you can do. Actually, it's very easy. It's actually corresponds to a conjunction. You can just take the intersection of valid statistical inferences on each one, but it's quite stringent, right? It's very, because all you need is one pipeline that doesn't give you a result at a given region, and then you don't have it. So yes, that's one way, but it's a very, very stringent way, and I think you'd oftentimes have no results. There's another question you want to have. Is it, I'll just use the order here as they're being voted on. Is it fair to find a consensus as all pipeline, or could it be that some are worse than others and should be excluded? Which one of you want to pick that up?
I can say a few words. So I think this relates back to that circle I was drawing earlier. I think there are many different reasons that creates this variability. So yes, probably some pipelines are worse. Maybe some pipelines have issues and we should exclude them, and we'll know soon that they are not good practices. Maybe some pipelines are not well suited for your data set. And I think this will need more work to better understand what's going on in that space and which pipeline we should keep when we do a multiverse.
All right.
Tom, I want to jump into one.
Yep.
Oops, sorry, there went that mic. That I think is really good. What do you think of the seeming incompatibility between multiverse approaches and other approaches like pre-registration? Like, that's a really good question, but I don't think they're incompatible at all. I think that when you are writing your analysis plan, when you are doing the pre-registration part of it, incorporating the different stage of the analyses and the different analytic points of flexibility, I think that should be part of your pre-registration plan.
Yeah, there are just two different ways of addressing this problem. One is to fix and make sure there's no vibration effects, and the other one is another venue in. So it's an alternative way. Question here.
God, that's so bright.
Okay.
I was wondering if you could go back to your presentation earlier, one of the early slides. I had a question relating to it.
Is it possible to bring up my slides? It was the talk for last meeting.
Okay.
Can you walk me through the slide?
Sure. It was one of the early ones with a diagram where you showed the whole brain results beneath each one.
Yes.
Okay, but if we
well,
wait for
why
that, I
don't
have
you start me,
another. I really like that one of the solutions for this problem or this issue is education and training, because I feel like we talk a lot about reproducibility, but I haven't heard understanding and correctness as part of it. And I worry that some pipelines could be reproducible but wrong. So there was the global signal regression early on. One of the arguments for it was it regularizes my data and everything looks more similar afterward. Now that's what it's going to do mathematically, and is that correct neuronally and helpful? That's a big decision in the field, but I think there's a lot of evidence that shows that's not a good way to uniformize everything and homogenize it. And when we don't know what the ground truth is, just reproducibility is not a good enough criterion. That being said, it probably is something that some of the variability has been, it existed for too long and not really looked at, so that's fine, but there are other considerations to not nail into something. If I multiply something by all zeros, that's very reproducible.
Yeah, no, you make a good point in that it is the job of the person constructing a multiverse analysis to only consider sensible, pipelines that someone would argue to use. So that's a good point.
For example, I think we talk about optimizing. There's probably a reasonable phase space of things. We don't blur our data by 30 millimeters. That's too much. We blur it by 4, 6, 8, and where within there's kind of semi-reasonable zones, maybe we like to say. Optimizing suggests that everything is going to get to zero, and I think there probably will be some kind of minimal or acceptable variability, but again, robustness. But I guess we're not going to get your image back.
It looks like we can't do
Okay.
it. I'm sorry. We'll do that afterwards.
Okay, but just the point was that when you show things as thresholded clusters, maybe a lot of the blobs overlap and some of them don't. Fine. When you showed that image and you said, this shows the incredible difference in results across these data sets, I looked at that and I couldn't tell any difference among them because they were unthresholded, and thresholding is really a large point of instability. So anytime you put in a dichotomy of something into your processing, something big can happen there. And that, it's chaos theory, fine, these things in phase space, but actually the way we present data could be done a lot better. And this is something that we've been working on over time, that a dependence on thresholds that's decreased reduces a lot of these problems and shows a lot more of the data. So anyways, I think that making data available for everyone to look at later is okay. The first pass that people look at in a paper is that figure, and that's an important thing to present in a very open and more honest way, which involves showing more data and a decreased emphasis on thresholds.
Yeah, it was a very good point. When we did the software comparison work, we were really surprised at how bad the dice was, because qualitatively it looks similar, but yeah.
This is the same thing in the NARPS study, where each NARPS group is actually only 54 subjects, not 108, because they divided them. And also in the Bowring works, those groups are 17, 19, and 20 subjects, right? That's a very small sample, and actually I think the results do look very similar across them even with that. So again, how you look at your data really, really affects things. If you reduce your dependence on thresholds, that reduces a lot of these problems on variability. But again, there are very good cases to look at other parts of variability too.
Yeah. Thanks, Paul. So do we have time? We have more. Oh, we're doing great for time. Do you have one question you want to jump on, or?
Can I take one? So at the end of this, should we all just do multiverse analysis, or can we still do one pipeline and be aware of the differences? Of course, I don't have a single answer to that, but at least I can talk about what I'm dreaming about. I'm dreaming about us doing one pipeline and being able to tell you, okay, you're going to do another 3, 5, and you're going to have to change this step and see what happens. And if it's consistent, then you're safe. If we could have something like this, that would be awesome. And I think this entails understanding better the different things that can vary and how much they impact our results.
And the audience?
Con?
Yeah.
Perfect. Follow up to the question. There's another symposium on the other side of the campus that is discussing how doing multiple pipelines and multiple analyses is not really the best idea. In other terms, not just statistical, but also it has other impacts on, for instance, environment and other things. So that was the question, actually. So can we actually just stick to one pipeline if we're, because there are negative implications in doing so many computationally heavy analysis. So.
Is that part of the environmental concerns?
It is.
Environmental
well, that's not the only concern, but it's also like we have a lot of resources.
Yeah.
There are other researchers that do not have as many resources as we are, and so that becomes just something that we can do because we have the resources to do it, but it's not open to everybody.
Yeah.
So those are also social.
So, and that's another, someone online. If we should be doing multiverse, how many should we be doing? So all I can say is that I know that there are people who are looking into this, and it's a really pressing research question, which is someone should do like a gazillion of them, many different things, and then try to work out which are the most important variants. So I hope in a year or two we will know, like, okay, well, if you're going to consider multiverse, here are the most important things to vary. And Angie already highlighted some that came out in the NARPs, and I think that's where we need to go. Question here?
Yeah, so I was wondering, do we always necessarily have to see the inter-software variability as a bad thing? Or could it be used as a positive thing? For example, if we do aggregations of the results of the different softwares, could this lead to something interesting?
Well, there is an argument to be made that the aggregation is more predictive, more generalizable. So that definitely, I think that's the central motivation. So were you thinking about something different? Because I think actually Greg Carr has actually shown that with his work, that you actually get more when you consider all the numerical instabilities and you aggregate over it, you get more generalizable predictive results.
Cool, thanks.
And do you want to do another one? Could a Bayesian approach to the problem of analytic variability prove useful in quantifying the uncertainty in the results? Possibly. So, I mean, one thing you might consider is that when you are considering a space of analyses to build and to consider, you know, someone mentioned that you wouldn't want to necessarily consider all equally, or you wouldn't want to do something silly, like absurdly, as Paul mentioned, you want to do like absurdly large smoothing kernel. Or smoothie, but you know what? How large is too large? How small is too small? You could imagine putting a Bayesian prior on what do you think is the most likely and least likely variance. But that itself could be hard. I don't know if either of you have any more thoughts on that. But I think there has to be definitely a level of agnostic. I mean, we're worried about all these different variants. If we knew a priori which was the ones, you know, we wouldn't be, you know, doing this. Could people move towards the middle? No, that's not. Here's a good practical one, because I think we're here talking about ways to integrate lots of different pipelines, and that's where we ideally want to get to, or someplace where we can get a small number of pipelines that approximate the full space of variation. But until that time, it's just one way. What factors should we consider if some pipelines give not exactly the same results? So let's say you can only run a few pipelines. Do either of you want to answer that?
Sorry, can you repeat?
What factors should we consider if some pipelines do not give the exact same results?
Factors in the pipeline? I think this relates back to what you were saying earlier. Like I don't think there is an answer right now about which factors are the most important, but hopefully.
Yeah, I think that's the central challenge of what we're facing. Question here?
I think this relates to some of these other questions, but a lot of this comes down to what fact, again, what you can conclude in each multiverse analysis. And it seems like the core principle has to be you're tweaking the same types of steps in pipelines. Because, I mean, using global signal as an example, I think it's absolutely wrong to compare, a consensus with including global signal and not including global signal, because that's a regularization step. It's a completely different type of step. If you wanted to compare global signal, you can include a multiverse with other regularization steps. But saying that the consensus between regularization and not regularization has any meaning, I just don't know how to interpret that. And so how would you think about approaching what to include and compare when you're trying to do this consensus approach?
This is the hard part, because you need to somehow have knowledge of the field and what is considered reasonable. So, I think that will be a large part of the kind of the science of multiverse analyses, is choosing that. But we may get to a point where we want to do some sort of, what is it called, an oracle exercise, a Delphi exercise, where the community should actually come to some sort of consensus about what are the variants that are reasonable to explore, and what of them do we agree are not best practice.
To add to that, I think there is also space to try and understand what the community is using. Like right now we have this very coarse description in methods, but if tomorrow we all share provenance, then we can actually know what people are using and maybe exclude part of that space because no one is using them for very good reasons.
Maybe we'll do one more question and then call it an end. You guys have any?
Can I?
Yes. Oh, please. Oh, yeah.
Yeah. So I was thinking that on this flexibility for utilizing different pipelines, and choosing a consensus is kind of, in my view, not really the best way to go for a pipeline, because in science the thing is to adopt different approaches. So we would be limiting the way we view the results. What I think is really lacking is the understanding of the methods being applied. So one possible solution for the whole community is probably improving the education of people applying that. Because a lot of problems in data analysis, in neuroimaging, come from the lack of understanding of the limitations of the methods and the applicability, let's say. So I would kind of, that's what we've been trying to do, is to improve education and kind of understanding of the real concepts in that case. So kind of broadening the perspective.
And that echoes what Paul said too, that you need to be educated in this. And certainly if you're going to do pre-registration where you commit to one single pipeline, of course that needs to be informed by the best practices. At which point I can plug the COBIDAS MRI and COBIDAS MEG reports as a reference. And just to say, a refreshing of the COBIDAS MRI report is underway, and that will soon be split up into lots of separate reports, one for each domain. For example, subjects, how to report, how you collect your subjects, how to do the image pre-processing, how do you do acquisition, how to report acquisition, and things like that. There's one here. An important common denominator between all your tasks is about training. But I'd add PIs need training as much as postdocs and PhDs. Yes, I think that's true. Sorry, that echoes on your comment.
About training, we have a comment from JB saying that he was suggesting that in that talk with Neurostar as well. So for those of you who don't know Neurostar, it's like a Q&A online platform that is open to everyone where people can ask questions. And as the community is asking more and more questions, this ends up being a knowledge space for everyone to learn.
Yeah, that's like a stack exchange for brain imaging. This one is maybe someone in the audience can answer, because I don't actually know the answer, which is, what are the expectations from funders like NIH towards supporting reproducible neuroimaging?
I did see that one, and I was thinking about it. I mean, I know in the study sections that I serve on, reproducibility definitely comes up, pipelines definitely come up, and I think that anybody submitting grants needs to address reproducibility somehow. But, study sections are variable themselves, and attention is not always paid the same weight across different issues, right? In conversations with NIH program, they would like to see more reproducible outcomes, and they're very interested in highlighting this aspect of the work in your proposals. So this is the time to get on this issue and to really think about the work that you're doing and to become familiar with the tools that are available and with the work that's emerging. And yeah, that's not just your grad students and your postdocs. These are the investigators, the PIs that the time is right.
Speak to your program officer, I think is the answer. Yeah, question?
I have one question. So as a student, we have some different supervisor for different projects. And I had some experience, not experience, an experience that the supervisor A have the pipeline of X and the other supervisor have pipeline Y. So what should we do about that?
I think there's no right answer to that question.
And then, and then the data is actually quite the same type of data. So, yeah.
Yeah. No, I mean, people analyze data differently. Did someone have an answer? Because that would be great. This is a really tricky one. First, you figure out who is paying for your doctoral studies, and then.
And for real, let's take a moment to talk to the PIs in the audience and say, please be cognizant of the power dynamics that are at play when your students come to you, when your trainees come to you with these really important issues, and be sensitive to the underlying hierarchy that we all operate within, and be open to these discussions, because our trainees, in my case, my trainees are showing me the way, and they are educating me, and I think that that's a really important dynamic to have.
Yeah, I think maybe the upside, yeah. I mean, maybe as a direct response, what you could say is if you went to your supervisors and say, do you realize how hot a topic reproducibility and multiverse analyses are? This is an entree into a very interesting direction.
Thank you very much.
Yeah. All right, I think I will close there, give you 3 minutes of your day back, and thank you all for attending, and we'll be here for questions afterwards.